What's up, engineers? Today we are diving into something that's everywhere around us, but most people don't even realize it: graphs. Now, before you think this is just another boring data structure, stick with me because graphs are literally the backbone of the modern world. And every time you use Google Maps to find the shortest route, you're using graphs. Most recommendation algorithms like Netflix recommendation system and other streaming services, they use graph algorithms. Social media showing your friends are friends of your friends, they're using graphs for that. And even the internet itself, it's just one massive graph. And in this video, we're going to skip the heavy theory and focus on the practical side of graphs. We'll learn the core principles about each function before in pseudocode and then implement it in Go from scratch. I'm going to explain why we make each design decision, when to use different representations in your structure, and how the big O complexity impacts your real-world applications. And by the end of this video, you will understand how to represent graphs in Go, when to choose between matrices of values, adjacency list, and adjacency matrix, why Go's maps and pointers make graph implementation surprisingly elegant. The methods that you're gonna learn is the AddVertex, the AddEdge, GetNeighbors, HasEdge, and RemoveEdge. The big O implications of every operation we implement, you'll also learn. Now, before implementing graphs, it's really important to understand the ways to represent graphs. In our case, it's in Go. And you've got three main approaches, and choosing the wrong one can not only be a pain to implement, but also have a huge impact on your performance. So let's start with Adjacency Matrix approach. And this approach doesn't need context because it defines the vertices and the edges. Think of it like a 2D grid table where each cell tells you if two vertices are connected. That means that an intersection between a line and a column represents if there exists an edge between two vertices. So if you have vertices 1, 2, and 3, you'd have a 3x3 matrix. And the position 1 on 3 tells you if vertex 1 connects to vertex 3. So the first index is the from and the second one is the to, right? And this will tell you if you have an edge between them. This approach might be great for edge lookups, checking if two vertices are connected is O of 1. However, this might not be ideal for sparse graphs. If you have 1000 vertices, let's say, and only 50 edges, you're wasting massive amount of memory, storing mostly zeros. So yeah, not that great. So not the best use case for your space complexity, which is V square. Let's see the big O analysis of this approach. So adding a vertex is a pain. So you will have a complexity of O V square. The add edge, check edge, and get neighbors, they're all O of 1, and the space complexity is O of V square. Let's now understand about matrix of values or value grid. And this approach looks like an adjacency matrix. However, each cell in the matrix is a vertex, which means it contains actual data. And edges are implicit based on spatial relationship. So how does that work? Edges exist between adjacency cells based on problem context. No explicit storage of edges. They are determined by their position. And the context determines valid movements or connections. And what is this great for? So this is what would look like an matrix of values or a value grid. So what is this good for? It's good for spatial problems. So let's say pathfinding games or 2D that uses a lot 2D or 3D grids, image processing, pixel neighborhoods, for example, maze solving algorithms, cellular automata, and another type of problem that this would be helpful with would be geographic or map data. So for GPS navigation on city grids, terrain analysis, resource allocation on maps. And the third type of problem that this can be really helpful with is with puzzle games and sliding puzzles, match tree games, board game AI, and much more types of problems. And let's see the big O analysis of this approach. So the big O analysis would be all the functions that we will implement today is O of 1, and the space complexity will be O of V, where V is equal to rows times columns. So yeah, as you can see, it's a much better approach than the previous one. Let's now talk about our approach, and which is Adjacency List. In languages like Java or C++, you typically use arrays or vectors to implement graphs, but Go gives us something beautiful, which is maps with pointer receivers, which makes everything easy to work with. In this case, each vector knows about its own connections. Think of it like a social network where each person has their own contact list. So this would be the structure like. The graph is the structure that will contain a map of all the keys of all vertices, and the vertex structure will hold the data of a vertex. In our case, an int value and the map of edges. And the edges structure, which holds the connection between two vertices. In this case, the weight of the edge and the destination vertices. So how does that work? When you access graph.vertices, you'll find any vertex in O of 1 to find. When you access the vertex.edges to find any vertex neighbor, it will be O of 1, and the edge destination, which is where the direct pointer to the next vertex, that's really fast operation too. We can see the big O analysis of this process. Almost all of them are, yeah, the AddVertex, the AddEdge, and the CheckEdge will be O of 1, and the GetNeighbors will be O of the degree, which, well, the degree of a vertex is the amount of neighbors that it has. So yeah, it's still pretty fast. And the total space will be O of V plus E, V being the vertices and E are the edges. Let's start implementing the graph. Now that we know the possible ways to make graphs in Go, let's understand step by step the logic of each function and then implement it in code. Let's start by implementing the basic structure of our graph. So here I am on my IDE, and one important thing to notice is that we are gonna make a directed graph, which means that an edge, when it have relationships, it will have a unique direction, a unidirectional, no, it's a unidirectional graph. So let's start by implementing the interface. I will use an interface for that. You don't need to do that, but I really like this because I can make a constructor to initialize this thing and reuse that, right? So yeah, I will have a type graph, which will be the structure itself. Let's have the vertex structure, which will have a value, which is an integer, and the edges map, which is an int to the edge. The edge itself will have a weight because you can apply weights for that. And the destination vertex, the vertex. So the vertices will contain a map of all keys of all vertices. And our vertex will be of key to edge, the key of the vertex key. So that's the basic structure. Now one thing that we want to do is a constructor for our graph, so we can initialize this thing. So this will be the basic structure for us, and we'll have an AddVertex here and so on. All the methods will go there. But how can you add a vertex in your graph? The steps to add a graph will be: the first step is to check if the vertex doesn't already exist, because you don't want to have the same vertex inside your graph. The step 2 will be to create a new vertex structure without any connections yet. And the third step will be to register the vertex in the graph, which is the vertices map. The pseudocode for that will be like that. So you first check the vertex, the vertices, the vertex exists inside the vertices map of your graph. You then create a new vertex without any connections, because you'll add the connection later on, maybe. And the third step will be to register the vertex inside the vertices map of your graph. So let's now implement this in Go. Let's first make the signature of our method here. I'll make a pointer method for that. And the first thing is to check if the vertex doesn't already exists. Return the graph if it does. So we can check that inside our vertices map inside this thing. And the way we can do that is by searching by this key, and if it does exist, I will just return the graph as it is by this time. The second thing is we create a new vertex without any connections. So this will be a pointer because as you can see on our structure, we have a pointer here. So this will be a pointer. And I start declaring the value of my vertex. And the edges, I will use a make function for that. I will not initialize as a new thing because I want to be able to easily add new edges later on. And if I don't do that, I will have to perform a make anytime I add a new edge. So I'm doing that right now. And the third thing is to register the graph. Register it in the graph. Is equal to our vertex, and we then return the graph. So this will be the AddVertex function. We first check if the vertex doesn't already exist. We then we create a new one and we register it inside our graph. Let's see how we can add an edge. But before we do that, make sure you leave it a like below and subscribe for more videos. If you're liking this video, leave it a comment down below of what you want to learn. And the adding edge function is an important one because it transforms isolated vertices into a connected network, right? And as we are implementing a directed graph, we'll add only one way. And the steps will be the step one is to check if both to and from vertex exists. The second step will be to check if edge already exists. The third step is to create the edge itself. And the fourth step is to store the edge. Before implementing that in Go, let's see how the pseudocode will look like. So the first step is to validate vertices. So we get the from vertex inside our map of vertices on our graph structure. The second step is to handle existing edges. So our approach can be to update an edge. So we first check if the edges on the key for the to already exist, which, well, the to is the destination, and we then update the edge. Else, which means that it doesn't exist, we then create a new one. The third step is to create the edge object, and the fourth step is to store in from vertexes contact lists are the maps of this thing. Let's now implement this thing, and the first thing I want to do is to make a helper function because we'll use that a lot, and this function will be to get vertexes. And we can check inside our vertices map from our graph structure, and if it exists, I will just return the vertex, and otherwise I will return nil. So I will declare this thing on my interface. So you will see that we'll have a bunch of methods on this interface. That's not really a great practice in production. However, this is only for education purposes and it's for a graph. You may not have like all the methods of a graph in production, and you may not want all the methods from a graph inside our interface. It will really depend. And we will have an AddEdge, which will have a from, a to, and the weight of this connection. This will be a pointer method. So the first step is to check if any of these vertices are null. We return nil on this case because there's nothing we can do. So the second step will be to create a new one or update the old one if it already exists. So if it already exists, I will first declare a variable, but if it already exists, we can check that inside of our map from Vertex Vertex. So I will get the from Vertex. So in this case, so let's see what we are doing. We have this structure here, which is our vertex structure. This is the value, and the edges itself, which is the map of edges that the vertex will have. So in this map, we have the vertex key, which points to the edge that this vertex have, and of course it can have multiple edges. So that's what we are doing, which we are checking if the connection doesn't already exist, right? And we are doing that here. We are checking on the destination vertex if it doesn't have already the key inside the from vertex edges. If it does exist, I want to update the old one. I mean, I can just keep the old edge destination because yes, we are literally checking that right here it does exist, so it will be the same destination. So otherwise, if it doesn't exist, we will create a new one. And the destination itself will be the two vertex. And the third step will be to store the value on the edges map of from vertex. So we return the edge. This will be the AddEdge function. Now GetNeighbors. This is a crucial function because it allows us to perform algorithms that actually can check for paths inside our graphs, like breadth first search or depth first search. And path finding, which are the options from this position itself, the shortest path to which explore all reachable vertices with their distances, and graph coloring algorithms, because to color the graphs you have to know the values of the neighbors. So the steps are actually simple. The step one is to check if vertex is null, or yeah, if it does exist. The step two is to get the connections, the edges of that vertex, that target vertex, and get each one key, which is basically the destination vertex. The step 3 is to extract each key, each neighbor key from the vertex and to push inside an array or list or whatever and return it by the end. And the pseudocode for that will look like that. It's not an hard function to do. So we first get the target vertex. If it's nil, we return an empty array, an empty list. We then get each key inside the target vertex edges, and we then return the value of this list, all the values of the vertex that the vertex is connected to. Let's now implement that in Go and see how this will look like. Now the first thing I'm gonna do is to get the neighbors, declare the GetNeighbors function, which will receive a vertex and will return an array of integers. So this will be a pointer method as all the other ones. And the first step, as we saw before, is to check if the vertex actually exists. So let's get the target vertex with our helper function. If target vertex is equal to nil, we return an empty array. So the second step is to check inside the map of edges on the target vertex. We'll declare neighbors empty slice, and we can range inside the vertex edges, and for each one we will append neighbors and the key of this thing, and we then return the neighbors. So this will be the third step, but yeah, it is what it is. So this is a really simple function because the way we implemented the structure itself, it makes everything so easy to work with. Now the HasEdge function will check if two vertices have edges between each other. So this is a directional graph, so it will check only in one direction. And the step 1 will be to validate if both vertices exist. So this is really straightforward. If any of them doesn't exist, you won't have a connection between them. The second step is to check the connection from vertexes edge map and search for the to key. The third step is to return the result. So yeah, really straightforward. And the pseudocode for that will look like that. It's actually a really simple function to implement. We get the from vertex, the to vertex. If any are nil, we return false. And we then check inside the from vertexes edges with the key being the to vertex, which means the destination vertex that we want to check. Let's now implement that in Go and see how this will look like. So this will be a pointer method to HasEdge from and to, and I want that to return a bool, which will tell me if it worked or not. So yeah, the first step is check if both exist. So from vertex will be check get vertex from to vertex true. So if this exists inside our from vertexes edges map, we will return true. So if exists, I just want to check if it exists. I don't want the vertexes value, the edges value. So yeah, if it does exist, we return true. Otherwise, we return false. So this will be how our function will look like. Now removing an edge is actually not that hard to. And the steps for that will be the first one to validate if both vertices exist really. And the second step to check if edges actually, if the edge actually exists, because if it doesn't make sense to remove it. And the third one will be to remove the edge. Let's see the pseudocode of that. And the pseudocode will look like that. You first check the vertices exist. The second step is to actually delete if it does exist. So we can do that in only a block of code to check and delete it, just an if else. And let's now implement that in Go and see how the code will look like. And this function will have the signature. To remove the edge, we need a from and a to. And I want to return a bool for that too, because if it doesn't work, I just return a false. So I will get the, let me do like I did before, check if both exists. So I will get the from vertex. Let me do like that. Sure. Now the check-in will be the same too. We can copy that too. So if it does exist, I will delete and from the map of edges. And the way we can do that in Go, we have a built-in function which is called delete. And we will get the from vertexes dot edges and the key itself, which is the to key, because we are deleting the destination in order to remove the connection. And that's basically it. I will make a function for printing this graph too, because I want to test this code with you guys. Print graph. If the graph is new, just return. And I will range inside of my graph vertices. And I will now arrange inside the vertex edges, because I want to see each one's connection. If the value is nil, it's not nil, I want to print the actual connection itself. Otherwise, we can print without connections. Sure, this will allow us to see much better what we are doing. Let's test this graph. The first thing I'm gonna do is to instantiate my graph to make a new graph. And let's add a vertex. Let's add a tree and add another vertex, which will be, I don't know, 5. And A1. Now, if we print that, oh, I haven't declared that inside my interface. Let's print this bad boy in graph. As you can see, we have a 3, a 4, and a 1 vertex with no edges attached to it. So let's create an edge. I will create from 5 to 1, and the weight will be, I don't know, 10. So if we print that, we can see that the vertex 5 is connected to vertex 1, and the weight is 10, right? And we can get the neighbors to I'll get the neighbors of 5. The neighbors will be 1, as we can see here. And another thing that we can do is to check if a graph have an edge. So graph dot has edge from 5 going to 1. We can check that, and yes, it's true. If I check 1 to 5, this will be false. If I check 3 to 5, this will be false too. We can check if the 3 have neighbors. It will be an empty slice, an empty array. So we can delete. Let's delete. Remove edge from 5 to 1, and let's see if this thing is working, and I think it is. And first, it has edge, true, has edge. After it's false because we deleted that. So yes, we can also print this thing before deleting, so you can see. And that's it for today's video. Leave it a like below and subscribe to this channel, and see you on the next video. Bye.